Thanks, Kavita, Daniel, for having me here. It's really great to participate in this workshop. So this talk is going to be about the same line of thought as what Fabrice explained this morning, namely when you have interaction through the control as well as through the states of the agents. But then the formulations and the assumptions and the results would be of different types. So yeah, this is also in the along this active line of work of trying to understand the convergence of the n-player game to the mean-field game, and here with Dylan from Zurich, we try to give our take on the problem. So I don't think I really need to motivate things here. So let's say I just want to present our notations in this talk. So yeah, present the generic n-player game. And perhaps the important notation is the Ln here, which is the empirical law of a given vector. So the boldface are always going to be vectors. And here, so we have the boldface X for the states and the boldface alpha for the controls. Otherwise, everything is pretty much standard. So we have this n-player game here. And typically, you want to understand are they equilibria, and when they exist, can they be, are they close enough to some mean-field game? What's the mean-field game? So these kind of questions. So you want to, exactly like I said earlier, understand the large population behavior of this game here. Good. So this slide also is pretty much what was explained earlier this morning and also throughout the week. There are well understood approaches to attack the problem in many cases. Fabrice talked about the compactness approach that works both in the closed loop as well as the open loop form of the problem. Then the PZA method that has been pioneered by people right in this audience that also works for, I believe, closed loop control problems. And recently with Mathieu, we started looking at it in sort of very probabilistic way and try to write down particle systems that characterize the game and try to understand their behaviors. And this, so far, we're able to do that only in the open loop case. And almost everything I'm going to do in this talk here will be based in the open loop case already only. And in the last talk, I'll make a comment on on some kind of link with the closed loop case. And there's also a recent work by Erhan and people around him where they try to continue this approach here in the case where you have a dense graph underlying the interaction among the players. So here we have a totally complete graph. There's no heterogeneity there. So perhaps the key word in our approach here would be weak formulation. So we really take that seriously and try to get as much as we can from this different formulation of the game. So we don't, in this game here, we will not look at this state process, but a weak formulation, a weak solution of that process. So the idea is typical, is that you imagine that under very mild assumptions on sigma and B, you can solve this controlled process or this controlled equation in a weak sense. Meaning that you can find some probabilities basis, some Bayesian motion on which this equation is solved, and then optimize over all these tuple here. So you say, I don't know exactly what the state space is, what the filtration is, what the Bayesian motion is, and then optimize over all that. So in this project here, we are going to make things a bit simpler and assume that we fix the probability basis. So this omega fp here is fixed, also as a Bayesian motion, so that is given, and there will not be, omega f will not change. And what will change here is the law of the solution. So the game now takes the following form. We assume that this process equation here is solved in a strong sense. So we have this uncontrolled driftless equation that we can solve. We now construct a weak solution to the state equation by Gisanov theorem. So by Gisanov theorem, the process P alpha defined this way here allows to derive a weak solution of a state equation here. And then when you find a weak solution, we try to optimize over it. So you see that here, X, the state is fixed, it doesn't change for the controls, but its law changes, and then that's what you optimize in this problem here. Otherwise, everything else remains the same. So one interesting thing about the weak formulation also is that, as opposed to the strong formulation that we tried before, we can allow pretty general dependence in the state process. So we're going to allow the state process to be path dependent. So we're allowed to depend on the whole history of the states up to a given time. And going forward, I will not make this dependence explicit. I'll just write B of X, but understand that we're looking at the history of time T. And also, if you look a bit closer, you see that here the drift right is just B, and here is sigma times B, because I should have perhaps multiply by sigma minus 1 here, perhaps drift 1. Here, I assume my drift is sigma times B to avoid having to introduce the inverse. Of course, perhaps I should also mention, so here in this problem here, when I write P alpha, so all the other players, they fix their controls, and then I pass over my control. So this law here depends on fixed values or fixed controls of other players, but only one of them is changed. So this should not fool you. This thing contains a whole vector, and n minus 1 of them are fixed, and n of them is changing. So what's the mean field version of the game in this case? So this is pretty much copied in a paper of Rene and Dan, I believe is a species thesis, where they studied this kind of games for the first time. So what you do is that you start by fixing some flow of probability measures for the state and the controls, this psi here. And you do the usual thing, you solve the game for that state, for that flow. So this you pretend this is the identity of what all the other people in the game are doing. Then you optimize you solve the problem to find the optimal control alpha hat here. And now you want it to be satisfied the fixed point condition because all the players would come up with the same optimizer. So at equilibrium, they should have the same law. So we say the best law I obtain P alpha hat. So this is the optimal value. Under this measure, the law of a state and the optimal control coincides with the one I fixed above. So this is the fixed point condition that you impose here. And again, I'm using different letters for A here because see, this A here is these are progressively measurable processes with respect to the n variant motions in this game. And here these are progressive measurable processes with respect to this one variant motion that I am considering. So call this W here W1, the first one in the system. That our goal would be the following. We want to say, well, let's say we can find a Nash equilibrium here. How does it relate to an equilibrium here? So I will start by looking at a simple example, just to convey the idea of the method, and hopefully that would allow you to see how things work. And then when I talk about the general case, it will be a tad more convincing. So I consider this example here where it is pretty much a linear quadratic example. So the energy here is just the quadratic norm of the control of one given player. I have here kappa 1 times the average of the states, kappa 2 times the average of the controls, and here just the absolute value of the state. And the measure of P alpha now is just a drift. So if I think of it in the strong formulation, then here I'm trying to control something that is sigma alpha I dt plus sigma dwi. Or essentially, in a weak formulation means that I'm just fixing Brownian motion because sigma here is a deterministic number. And I put the dimension to be 1. In this specific example here, as well as, the mean field gain would be similar as above. So I again fix some flow of measures for the states and the controls. I solve the standard control problem and I impose a fixed point condition. So this is exactly the same as above. Now, the approach that we are going to use here is the following one. So we can delineate it in a 3-step method. The first one is to say, well, let us be given a Nash equilibrium. And in that case, a bit like in the PDA framework, we try to find a way of characterizing it, solving something that looks like an HDD equation. So here we're going to try to identify what I call a relevant interacting particle system to characterize this Nash equilibrium. In the second step, you do the same thing for the mean field equilibrium, and you try to compare two particle systems. So that's essentially the approach. I'll go through this step by step. So first step, let us be given a Nash equilibrium. There might be many of them. Let's believe that some way we have been able to find one Nash equilibrium. I'm calling it alpha hat I here. And so the approach is now where we say, by the very nature of Nash equilibrium, if I fix what other people are doing, I look at my own control, then this becomes an optimal control for the game. So I freeze all of the other controls and I consider a standard control problem. Now I use approaches from probability theory. I think what I learned this from papers by Nizar and Jen Feng. So what they do there is to say, well, we define some dynamic version of the value function, you do DPP, and then instead of deriving the HDD equation, you rather do mathematical principle. So you say that this dynamic version, it's a super martingale for all process, for all controls, but the martingale for the optimal control. And that allows you to derive, to say that the optimal value alpha here maximize the Hamiltonian. So this term here, this big term is the Hamiltonian. The blue part is nothing but the running cost in this game. And the red part here is the drift times the adjoint process. And this black part is, again, the drift times adjoint process. But here, I just isolated the term coming from the effort of the other players. So the ZII, so this is the diagonal element of this matrix that I'm going to talk about in a minute, multiplies my own effort, and the off-diagonal term multiplies other people's effort. So this is essentially the Hamiltonian in this game. And the statement is that if you have an optimal control or a Nash equilibrium, then alpha I here has got to be a maximizer of this Hamiltonian. In this case, we can write it explicitly. So the Hamiltonian here is given by ZII over kappa n over 2. So remember, kappa 2 here is a term that is in front of the control interaction. So if they want control interaction, the kappa 2 equal to 0. And I use that example just to also show where the difficulty lies when you add this control interaction in the problem. So now what is this Z? So Z is, like I said, comes from some type of adjoint equation. It solves, it's such that Z yi and this matrix, they solve this equation here, which is essentially a backward SDE system where the drift is the maximized Hamiltonian. So it's the maximal Hamiltonian in the problem. Good, so now I can simply plug in. I can do this process here, not just for alpha I, but for all of the other optimize the other elements in the Nash equilibrium. Then I obtain this system and I plug those values in this maximum drift here to obtain now a cleaner form of the backward SDE. So let me perhaps write it in a nicer way. So what I've achieved so far is that I said, let us be given Nash equilibrium. Then this Nash equilibrium has got to be written in terms of Z, where Z is the solution of this multidimensional system. It is what I call the relevant interacting particle system in this case. So even though here alpha is given as a very simple function of Z plus a constant, I will go ahead and give it a name just for future references. I will call this lambda of Z and some quantity Aleph. Although I don't see these extra diagonal terms, I don't see it here. I just write it here for the moment because it would pop out later when we look at the general term, the general case. Just so for references, understand, we see that the optimal value or the optimal control is written as a function of the diagonal term of this equation plus or with some other term. And this function is important, this function is fixed, right? This is a given fixed function. Good, so let's try to play the same game for the mean field game. Sorry for the pun. Assume that we're given a mean field equilibrium, a unique mean field equilibrium. So this unique mean field equilibrium, if I also go through the definition as fixed, some flow of measures, and I do exactly what I explained from Nizar's and Jen Feng's work, I'm able to obtain the characterization, namely, it is optimizer of the Hamiltonian along some backward SDE system. And here it's not the system, it's the one equation because of the fact that all the other players are assumed to be fixed. So the idea is really the same. This essentially this part here and here, you phrase them, you take some arbitrary law, you write down the equation, and then you say, well, I want the equilibrium to happen, namely those abstract values should coincide with the mean of X and the mean of the optimal process, and you plug it here. If I had the more general setting, this Z here would be something that contains alpha. I mean, mind that this alpha hat here is exactly Z. That's why I have it here, not something more complicated. And again here, you see that the mean of Z comes in where I have kappa 2 because of the punctual interaction. Otherwise, I wouldn't have the mean of Z here. So let me say a few words about the equation. So the equation here, if I replace this term and this term by constants, by constant numbers, then it would remind you of equations derived in the work of Dan and Rene. Here, we go one step further and say, after deriving that equation that derive, I also build in the fixed point condition, right, to obtain this equation, which is not essentially a standard backward STE because here the driving buoyant motion is part of the solution. So driving buoyant motion here depends on Z, and the underlying measure here is written P alpha most surely, where P alpha also depends on Z. So it is like I have the equation and I build in the fixed point condition. So this equation characterizes the mean field equilibrium. And so for the convergence, I think we have a version of the paper that's online. And in that version, we say that to get the convergence, we assume that the system has a unique solution, and then we're able to pass to the limit. But mind you, this system solving is equivalent to solving the mean field game. So this is exactly the same as saying that the mean field game has a unique solution. Good. So this is the second step, and the first step, as you imagine, is to show that this particle system will converge to this one here, and a close observation of the particle system shows you that if you pretend that this blue part is not there, then you want to imagine that in the large population limit, this will have some type of Laplace number given the mean here, and some type of Laplace number given the mean here. And you expect also that in the limit, like what I call the extraterminal terms that characterize the effort of other players would vanish, right? So that here, the extraterminal terms would vanish, only the term Zii will stay there. That's why we end up with just one buoyant motion. Yeah. And so the idea would be to say that, well, let's, in the first step, show that this system here is closer to some auxiliary system where I do not have the annoying term here, then prove propagation of chaos, and then that will be finished.
When you speak about propagation of chaos, under which probability?
A very good question. That's an interesting question. So here the relevant probability measure will be P alpha hat, this limiting probability measure here. And that's exactly why when I pass the limit, the mean that I have here with respect to the mean P alpha hat. And I can do that because I've already assumed that the Nash Equilibrium mean equilibrium exists and P alpha hat is well defined, so I can use that. And along the same lines, what you would probably say is that, well, here I have a positive sign, here I have a negative sign, some doesn't really add up. It's because of Gisanoff theorem. When I change this to the, when I change this to the alpha hat, there's going to be a multiplicative term Z here that will minus, and this will make it the minus here. So it's essentially why Francois' question is important.
So in this simpler example, I guess the blue terms do not depend on the other ZJs for J different from I, and they normally would?
Exactly. That's exactly why I put this Aleph term here, where I put the ZIJ. In a simple case, they're not there. And what I explained about introducing the auxiliary system is not really important in this case. But in the general case, it would really be a difficult part, because here, this term here would be more complicated and would contain these extra diagonal terms. And I really have to try and prove that they go to 0.
And related in this average here in the second to last line, should there be a J on the Z? Because those are Z-I-I-N, or is it?
This is Z-I, this is JJ, sorry, that's a
JJ.
very stupid typo. Thank you for that.
Okay.
This is J and this is ZJJ. So I'm looking at the diagonal terms of the Z's.
So they're not decoupled then, these equations.
That is a very good point. No, this is, I don't know if people online can see that, but the Z in the mean there is really the mean, the average of the diagonal term, right? So this is really the ZJJ. Because here I have alpha J and I'm plugging their effort. Okay, so well, I would, the last step is production of chaos. It is not as hard to do in a simple case, but I think I will not really go through that here. I'll just, I mean, I hope that you will be convinced that when I change the measure from this here to alpha to W alpha, I get something that should converge, but I will not do that here. What I rather do is to just make one point, which is that in the abstract result or in the general result, I would assume that things are Lipschitz. And you might say, well, in your example, you had quadratic terms here. And how do you reconcile that? For this example, for instance, you will see that if you stare at this equation long enough, you will, for a BSD expert, you will see that you can show that this Z is going to be bounded. And therefore, this locally Lipschitz function here should be Lipschitz. And the idea is to say, well, this part here and this part here, they are deterministic values. So if I differentiate this process in the Maillard sense, so this is just wiggling the Brownian motion that underlies the process, then I obtain that this is, well, let me pretend the absolute value is differentiable. Then I get here the sine of x times the Maillard derivative of x, 2 times z, the derivative of z. The deterministic part goes away, dt, and then I get here the derivative of z to w. And well, looking at this equation, so this term here shows up here, so I can use this drift to do a change of measure once again. I obtain that this has got to be the expectation of the sine of x with respect to some new measure here. Essentially, this is the idea. And well, in this simple case, x was just Brownian motion, so it derivates to the sigma. And finally, you remember, I mean, for the BSD expert here, the idea is a bit like in the PDE case, z is what's the gradient of your value. So this is z. Right? So this is the so-called trace of the Maillard derivative that tells you that, well, z is bounded, so I can pretend as well that my generator here is Lipschitz and treat it as a Lipschitz function with generator. Of course, this might be general true all the time, but at least it's a convincing example that assuming Lipschitz continuity is not far-fetched. Okay, so with that, we get the result, which is that under the limiting measure, under the optimal value, we get that the Nash equilibrium converges to the mean field equilibrium at this rate here. So this rate here comes exactly from the rate of the convergence of this term here to this term here. So it's essentially that.
I have 2 questions. The first one is, can you come back to 2 slides before? When you have the change of probability measure for a given capital N, I'm just a bit worried of the fact that it depends on all the players. You can control this uniformly with respect to capital N. I'm just worried about this. You have some, because you say you have propagation of chaos under the P alpha hat or under the P alpha
hat, yeah. And P alpha hat
depends on N. So
no, P alpha hat is the mean field limit. And
this is the mean field limit.
Yeah, it doesn't depend on N. There's no N here. And this W, call it W1, so that it is independent of the other W. So when I do change of measure, only the Z1 survives, the other Z's will go away because of the fact that they're independent. There's no common noise here. I mean, because after that, I will just repeat these things in a more general setting and it will go a bit faster. So okay, so we get the rate here. Of course, you don't expect to have something like that in the general sense, in the general case here. This is just because we have this nice end here that made things go through. Okay, so now I'm going to discuss two things for the rest of the talk. I'm going to talk a bit about this assumption here, that we assume that this game has a unique Nash equilibrium, and I say it's equivalent to solving this equation. So I'm going to say something about solving this equation, right? Under which condition it makes sense. I can already say that we will not solve it in its generality. We are going to make more strong assumptions to solve this equation. And then I will conclude by talking about the limits in the general situation, presenting how to write the assumptions to make this work. Okay, so come back to general setting and look at the well-postedness problem. So the hypothesis, the condition that we make are that we assume that, so remember, this was the drift, this was the cost function, the running cost, and we look at this Hamiltonian here. This A here above was taken as R, so this is a set where your values live, the controls. And I assume that we can uniquely solve it, so we can find a unique maximizer for this problem. So far, this is not really such a big assumption. The hidden one is the one I put here. So the one I put here means that, so this psi is a measure on the product space, right? This is a measure on the product space. And I say that I want my maximizer to depend only on the first marginal of this measure. I don't want it to depend on this A. So essentially, in the literature, this assumption that shows up implicitly, but because people assume that they can split the B so that the law and the control, they don't interact. And if you have that, then you have exactly this satisfied. And then I importantly assume my control alpha, the map lambda, to be Lipschitz continuous. So here again, this shows in the literature in that if you have that this Hamiltonian is strongly convex, then you can also obtain this kind of Lipschitz continuity of the controls. And I assume, so here I can take sigma to be state dependent, B and G terminal cost and F are similar to be all Lipschitz continuous functions. And I assume B to be bounded, right? So I make these assumptions here. So, okay, so I make these assumptions here, and I also assume to have linear growth. So I need to have some growth property to guarantee enough integrability of all these things. So B's boundary is fine, but these guys here, F, sigma, and G should grow at the linear rate. At least in other variables, in X, they can grow at a faster rate because X will not really have one moment. So for X, it's really a big problem. Okay, so with that conditions, we have the following result. The result states that, well, quantity is small enough, then you have a unique solution. And this quantity essentially says G, the norm of G. So G is going to be bounded here, it has small enough norm, and that its Lipschitz constant are small, then we have a unique solution for the problem. So I printed this result a couple of weeks away in Chicago, and Pierre said this is not optimal because G bounded doesn't really mean anything, because if you add a constant to the game, it should not impact the equilibrium, right? So I think this is more an artifact of our method that we want to make something constant, something small. I guess that the terminal value is going to be small. But then we have not posted that part yet on arXiv, but we have been working on this to extend it. And what it turns out is that if we allow this G to be regular enough, so you can apply Ito's formula to this quantity. So we are first of all assume G to be state dependent now, and the law. So if you can apply Ito's formula in this interdimensional space, then we can relax this condition here altogether. And I'm going to talk about it in a minute. So we have to, the idea is, like I said, solving a mean field game boils down to solving this equation here. So I already presented that above in the simple case. So we want to solve this equation here and observe that here we have the law with respect to the new measure, right? And it contains a law of x in the problem. So to solve it, yeah, in the strong formulation, when x is controlled, you have a forward-backward system here, and allowing to have the weak formulation only allows us to decouple the system. So we don't have a forward part here, given that it is fixed, but it's not really entirely. It doesn't really make the problem go away because the law now changes. So it's still like a forward-backward system, so to speak, because the laws depend on the unknown. So, so if we manage to solve this equation here for G small enough, then the next step that we didn't do before is that now we can apply Ito's formula and write this in terms of some dt term and w term. Observe that the drift here doesn't depend on y, which is an essential thing that allows us to extend the result. Then we separate, we put the G at time t here, and the dt term here, and the Brownian part with z. And then we write down a new generator. We assume that this generator is Lipschitz, whatever is needed on the derivative of G to guarantee that, then we get the solution. Of course, you need quite a lot of regularity on the, you need to differentiate it at least 2 times, and you need the second derivative to be Lipschitz. So there's kind of a bit of regularity is needed there to remove this condition. Now, without that, I don't really know what to do. If it's possible to do without this regularity, and also, yeah, perhaps using a different method can allow us to remove this condition. This is perhaps because of the bound we use in our estimation, but so far it's just the best we have been able to come up with. So that's for existence. Let's now finish up with the limit. So for the limit, well, I think I've talked about this already. The steps we try to write down in terms of some particle systems whose proportion of chaos we study, and the ideal reference measure in this case turns out to be the limiting measure for the optimal control. Okay, so the assumptions are as follows. Remember the Aleph that I introduced? So it is known here. We assume that we can find a mapping, lambda, that maximizes this Hamiltonian. So this part here is the normal Hamiltonian of the problem. This part here comes from the effort of the other players. So this is the off-diagonal terms, and this is the effort of other players that shows up in the n-player game. And we want, the blue part is important, we want the mapping, when I take Aleph to be 0, to maximize the Hamiltonian that I had here. That I had here, right? This allows to identify, just by identify the n-player game and the mean-field game when Aleph goes to 0. So we don't want this mapping here to depend on n. We want it to be so that when I put 0 here, when I manage to show this off-diagonal term goes to 0, I end up with the limiting value. And again, you see that here, there is also this assumption that the empirical measure of the controls do not show up in the optimizer. So somehow we have again this splitting of B and F. And by the way, in that case, when you can split B and F, this Aleph can be computed explicitly. So you can really write it down in terms of the derivative with respect to the measure of B and F. So we don't do it here, but if you can split B and F, you can really compute Aleph explicitly. Okay, so and then apart from that, we want G and H, so the Hamiltonian of the true limiting system to be Lipschitz continuous, be bounded, and you want the mean-field game to have a unique solution, or alternatively, or equivalently, we want the system here to be solved. Okay, so when you do have that, then the first step is to show that, well, if alpha is a Nash equilibrium, then it is characterized as follows. So this is exactly the same as in the example that I had before, where Z here along with Y saw this system. The interaction is through the diagonal term, and the alpha here contains Aleph. So this Aleph doesn't go away. So the off-diagonal term, they don't disappear in this example, like Dan pointed out. In the example that I had before, they go away. And by the way, when I don't have control interaction, like you saw in the example, let me go further back. This annoying term is in terms of kappa 2, right? Which is the control interaction. It turns out that this is really where the difficulty in this thing lies. Okay, so we have this characterization result, and then we prove propagation of chaos with a given rate. So the rate here is Rn comes from showing that Aleph goes to 0, and its gamma n is essentially the rate at which the empirical measure of IID values should get lost. So if we have here state-dependent components, then this rate is known from Fournier and Brilliant's work, or from if you also have some function inequalities like log-to-Sobolev or Talagram on the limiting measure, you can also derive some rate of convergence there. So here we stopped here. We didn't make further assumptions, but essentially you don't have general convergence rates, but on some further assumption you can get a rate. And then using the fact that the off-diagonal terms go to 0, and importantly, the fact that the mapping lambda that we have here doesn't depend on n, so it is the same that maximized Hamiltonian, we are able to bootstrap the progression of chaos to get convergence of the n-player game. And I didn't say it before, but this y here is essentially the value of the game as 0. That's why we also get the convergence of y for almost for free. And same thing, v here is the 0 value of the backward SDE of Machinus of type. Okay, so so this is the main result of this work here. So I think I said it before when I was computing these things here, the Lipschitz continuity conditions can be relaxed if we assume enough Malevin derivatives of the coefficients. So in this case here, things were simple because the terminal value was simply xt. If it's not, then we want that this Malevin derivative is bounded. So this can be checked in some cases and will not be checked in other cases. But I mean, these conditions here can be relaxed. So something that we try to do, and Dylan was especially pushing for that, was to see if we can prove convergence here t by t, not just the whole process converges. And it turns out to be not a simple question. So we had to impose much stronger reliability conditions, like differentiating things like at least 2 times, apply to for many times to be able to get that this alpha n converges to alpha, not for all t, but for almost every t. So this is turns out to be a bit complicated, and this is also built upon similar ideas. So you essentially try to differentiate all these things in the Malevin sense and identify the trait of the Malevin derivative, and you end up with a new system with respect to the derivatives, and then you also to prove bunch of cases for the derivatives. That's why you need so much regularity. Let me close up here. I have a couple of minutes to conclude here. So this perhaps is to relate what I'm presenting here with Fabrice presented earlier this morning. And this slide come from discussions with Dan. We had a long email exchange on that. And the idea was to understand if in a weak formulation, strong and open loop and closed loop formulations would be the same. And our take on the question is the following. So maybe just a quick reminder of what Fabrice explained. Here in a closed loop case, you want alpha to be a function of the states. And in principle, you expect that it should be what you do in practice. You want to know where the other people in the game are before making a decision, not just what the noise is, right? So in this case, the equilibrium in the n-player game is not essentially easy, like he explained, because if I say the other player changes strategy, then it should affect their state and therefore my strategy, right? Whereby in the open loop case, when they change their strategy, it affects my strategy, but not my state, but not my strategy. The interesting thing is that in the weak formulation, X is uncontrolled, so that when they change their strategy, it doesn't impact my state, right? So that if you have the same filtration for X and W, the weak formulation, no, the closed loop equilibrium and open loop equilibrium turn out to be the same, and therefore we can also get the result that we have here for the closed loop case. So, but of course, this is not entirely the same as what they had in their, I mean, what they study in the papers, because they were controlling the law of the process, not the states themselves. So this can certainly change things. So this is about all I had. A quick summary, I talked about characterization results for the game in the end-player version, the mean-free game version. I show how convergence, how propagation of chaos allows to obtain convergence, also non-Markovian case. And I had this quick discussion. I hope it was convincing enough on the closed equilibrium. That's all I got. Thank you.
Okay, thank you very much, Ludovic. Are there any questions?
Just a clarification, I missed the point. In the second part, you still assume unique equilibrium as a limit, right? I mean,
yeah.
And do you have, okay, so I understand that you have this smallness condition that's,
for the existence.
For existence and for uniqueness?
Yeah, for existence and uniqueness.
So you build that by what? By Barnard fixed point theorem?
Yeah, we apply Barnard fixed point theorem. Yeah. That's why we need it this much, because when you perturb the processes, you define this mapping, you want it to be a contraction. And to do that, you need to have some smallness. I mean, something has to be small. And it turns out that here, everything can be grouped in a terminal value, a terminal condition, and that's what has to be small.
Yes, and if you are assuming that the time horizon is small, it works the same or not?
Nice point. So here we observe that. So here, first of all, by Lipschitz here, I meant Lipschitz with respect to the sup norm process. So what we observed was that if we assume that G is Lipschitz with respect to the L2 norm, then T small and the norm small was enough. So we needed these two to be small, but not LG, the Lipschitz norm of the terminal condition. And this is essentially not so hard to see, because you just bound this norm by T times the other one, and then you obtain that. So it's really, yeah.
Thank you very much.
It turns out that this is a bit puzzling, because even in that case, we still need to have this to be small.
That's weird. That's really weird. Okay, thank you very much.
So just to be clear, you only need the smallness condition for existence and uniqueness, but if you assume you have existence and uniqueness, then you get the convergence without any smallness assumptions?
Yeah. Okay. So for the convergence, it was not needed. And this part is also not so hard to see, because so the xi's, they're essentially IID, right? Because I don't control anything. And then when you try to show convergence, this is the empirical measure of this entry again. And you have here the limit. You see that when you compare the particular systems, essentially you will compare this one and this one, this one and this one. So this kind of goes away for free, right? But for existence, it turns out to be more difficult, because here it depends on some law that you perturb. And then when you perturb this guy here, you have to make it small to have contraction. That's why all the smallest conditions appear.
But just given one solution and
a unique one, it needs to be unique, because otherwise we cannot prove.
Yeah, but there is no stability conditions on the game itself. This is what you say.
Yeah, sure.
Yeah, and maybe I've kind of follow up, but very maybe too general question. But like for instance, if you assume that you have two solutions which are quite distant in some norm.
For the mean field game?
Yeah, for the mean field game. Okay, can you say something about the local stability? Can your techniques be used to
So
in some sense, it's a bit related to the question of François, because I think that because you assume you have existence, and if you have existence and uniqueness of a mean field equilibria, in some sense, you show some stability around this in the n player limit. You have some stability for this solution, and so I was wondering if you.
No, we didn't study.
We
I mean, we didn't study a case where you have many solutions on instability. I don't want to say anything wrong here. I don't know what the method would say. I didn't study that.
In this multi-formulation, the Brownian motion is a part of the solution. So you need to assign the.
So this is essentially Francois' question. So,
Yeah.
So here, because we have been given the main field game solution, this becomes, so to speak, the true measure on which we work. So we transport everything on that measure. And in this case, B is essential because the zero set with respect to P or to P alpha are the same. So having quality surely and P alpha surely would not be any different. So yeah, so essentially to prove limit convergence, we go back to P alpha and then we prove everything there with P alpha. And that's why we get this inequality here. I mean, so it's this P alpha law of the X under the mean field equilibrium. But the P itself, we don't write things out of P itself because if you want to P, you can, of course, do Cauchy-Schwarz and P, but it seems to be natural to write anything with respect to P alpha because that's with respect to what the laws, if you remember the mean field equilibrium condition, the laws have to coincide with respect to this P alpha. Or did I misunderstand the question?
Okay, let's thank Ludovic once again and all the speakers of this morning session.